Hey guys, I decided to make a movie about a gambler's fallacy because Adam was talking about this last night. And although my mathy talk might not convince him of anything since he has a fundamental disbelief in math, um, I figured I might as well give it a shot. What the gambler's fallacy is that say if somebody gets three heads in a row, that this next flip of a coin would be more likely to be tails than heads, when actually it's still a 50-50 chance. Given that these have all happened, you still have a 50-50 chance of getting heads and tails in this situation. But a lot of gamblers, um, a lot of people in sports um, have this fallacy that it would be tails. Actually, in sports, they have kind of almost the opposite mentality, especially in basketball. Um, they'll have this idea where they make a shot, they make a shot, they make a shot, they make a shot. And so they have this idea that they are having a good day. They're feeling hot. And they think that this next one, they have a higher probability of getting a shot versus missing. And that's just wrong. It's I'm sure there's some different circumstances where people have bad days where they're um, they didn't get good sleep or something and they're not prepared for the game. But they did a statistical analysis at some point, I don't know who, um, and they found that if somebody was on a streak, they were equally likely to miss the next shot at any point along the streak. I don't need to get into that. All right, so the gambling fallacy, um, if I want to try to prove it, one good way to show probability is through these things called simulations. So we're going to make a simulation where every time I get a 1 as a random number, it will represent getting a head. Every time I get a 2, that will represent getting a tail. So I can go over here. I'll take random numbers between 1 and 2. And for this particular exercise, I'm just going to do 3 values. So what that means is I'm flipping a coin 3 times, and it can either be a head or a tail. So in this particular instance, I have a head, and a tail. Now I'm going to fill out 2 different tables. One table is we're going to find the probability of, or the simulated probability of getting 3 heads. And so if it's not 3 heads, we're going to put a dash over here. Now, given the fact that it's 2 heads, I want to find the probability that I get a third head. So that would be 1, 1, 1. And, or given the probability I have 2 heads, what's the probability I get a tail? Well, this is a good example because I got heads, tails. And the gambler right now would be really excited because he is correct in that for this one particular roll, or flip of the coin 3 times, that he got heads, and then he got a tail. So now if we do this again, now he did get all 3 heads, head. So we'll put 1 in each of those columns. And now I'm just going to keep on hitting enter. I'm going to do it 3 times. So this one is 2, 1, 2. So for 2 of these, they didn't get heads all 3 times. And one of them, they did get 3 heads. And then for our second box, there's 1 here, and that's it, because there's no times where you got 2 heads and then a tail. So I'm going to hit that 3 times, so we get our next 3 data points. None of these got 3 heads, so I can make 3 dashes, 1, 2, 3, and none of them will go in here because I didn't get 2 heads the first time. Now here, all of these go in the not getting 3 heads category, And there's one situation where I get given 2 heads, there's 1 tail. Now hit enter 3 more times. So I have 2 where we got 3 heads. And so that's given 2 heads, I get a 3rd head. And this one just goes in the not getting 3 head category. So as you can see, being a statistician is super exciting, just hitting the enter button 100 times. They would have a better method for doing a computer program to simulate a million of these, because even as I'm doing this, so 112 is over here. There's none that are all 3 heads, so this is 1, 2, 3. Even as I'm doing this, there's such a small sample size that there's going to be some variation in what I'm getting. So these are all 1, 2, 3, and none of them were heads. So this small of a sample size won't be perfect, but it could give you an idea of what's going on. All right. For right now, we can just stop here. I could do this forever, and they'd be closer to the real probabilities. But in this case, the probability of having a head, and a head, so that third one was a head, is going to be 4 sevens. We're getting head, tail would be 3 sevens. So given the fact that these two are already set in stone, there is a simulated probability of 4 sevens and 3 sevens that is going to go to tails. If I increase the number of times I do this, which would bore you guys considerably, these should turn out to be equal probabilities. And the reason why I have this first table is Adam said, well, isn't there a 1/8 probability of you're getting all 3 heads? Well, in that simulation I did, we have 4 out of, what's that, 19? So the probability of getting heads, are simulated as 4/19. So let's see how that compares. That's about 0.2, and 1/8 is 0.125. So my simulated probability was 0.21, but my actual probability, it is 0.125. And if I would have flipped this coin, a lot more times, this would have driven down closer and closer to 0.125. All right, so now it comes to what we really care about, is risk. Now in risk, people might think they're getting screwed, or they think they're on a hot streak or something based on their probabilities. But I just pulled this random chart off the internet. And this is saying, this up here is how many losses, every time they lose. So they lose losses there. Here the defender loses 2. So if the attacker is attacking with 3, the defender has 2, there's a 0.372 chance that the defender loses 2, and a 0.293 chance that the attacker gains 2. Now how we would simulate this is we would go back to probability. We'd do random integers between 1 and 1,000. Oh. And then let's say we're going to attack, maybe 8's too much, let's do 6. Say we attack 6 times. So in our first one right here, 0.997, that means that the attacker, I should define this. So my numbers 1 through 372 will mean that the defender loses 2. 373 to, I have to do some basic addition, 373 plus 336, 709. Oh, I'm sorry, 708. And then from 709 to 1000, then the attacker will lose 2. So in this particular instance, the attacker loses 2. Then he loses 1. They each lose 1. The attacker loses 2. The attacker loses 2 again. Then the defender loses 2. So we can simulate this many times, and in the end, it will come out to these probabilities, hopefully, assuming that these are correct on the old internet. But in the short run, it's possible to get a streak. Like that one was actually a pretty bad streak for an attacker. The attacker lost a few times. But it's roughly a third, but there's a higher percentage chance when you're attacking than when you're defending. I don't know. I'll be quiet. I thought I'd make this.